to how I was taught that. Well, that's it. And actually, beyond period to how I was taught that. Well, that's it. And actually, beyond period.
So my name is Megan Heenehan. I'm at Eastern Connecticut State University. And in the fall of 2014, I taught my very first ever IBL course. It was a graph theory course. And so I kind of just wanted to gauge how the students were feeling about the method. None of them had taken an inquiry-based learning course before, and so I wanted to measure their feelings and kind of make sure that they were having a positive experience. So my poster just kind of shows how, initially they had a pretty negative or not so sure about the method kind of reaction, but as the semester progressed, you can see by the final, almost everyone had a very positive reaction to inquiry-based learning. So this just kind of sums up some of the things that they were saying about inquiry-based learning, some of the things they liked, some of the things they didn't. But overall, took a little convincing, but by the end of the semester they were pretty happy, and most of them said they would do an inquiry-based learning class again.
Our idea here was that we didn't want to overwhelm the poster with written words. We wanted to say, here's what's being done, and we have the actual materials that we talk about in terms of the written materials. There's some examples of the professional development we've done, of everything we've done, and it's really the spirit of inquiry-based learning to be able to actually hold something, look at something, see what we think about it. And we've gone a long way at UT to creating a base of active materials that can be used. And we wanted to convey that with the poster. We wanted to show how much interaction is done, how learning is really in the student's own hands. So we brought a sample of an example of the blended methods and the online technologies that we use. This would be from an edX profile. And it's just a quick video going through how the program works, what students are able to do, what students are able to see. The idea of this is to reach a broader audience, be able to talk to more students about topics in mathematics and give them more resources for the students who are in classrooms to deepen their understanding of the material.
I'm Nina White from University of Michigan.
Dan Visscher.
And we were looking at using oral assessments in conjunction with traditional written assessments in a course, an IBL course for future elementary teachers on number and operation. And two of the questions we were asking were what student characteristics might cause some students to perform better at written versus oral assessments. So that was one question we were asking. And the second question we were asking is, what opportunities for learning can oral assessments in themselves provide? So thinking about assessment not just as a way of extracting what a student knows, but actually being part of the learning experience.
Yes, one reason that we were interested in doing this is that we found a lot of students on written exams would get stuck at a certain point and wouldn't progress past that point. And so despite the fact that we saw them in class demonstrating knowledge in groups, talking with each other, being able to make progress, when they got stuck on an exam, they sort of didn't get any further and they got a 0 on a problem. So this was one area that we were interested in, probing a little bit deeper by giving oral assessments. What we found was that students so we gave an instrument that kind of rated how much mathematics anxieties students had, and we found that this had an effect on their kind of comparative performance on written versus oral assessment. And so we distinguished a little bit further between different types of math anxiety. In particular, we have 2 parts: explanation anxiety and problem-solving anxiety, and kind of different effects on how you performed on oral assessments versus written assessments. If the student had more problem-solving anxieties, then in fact they ended up doing slightly better on the oral assessments, largely due to the scaffolding that we put into our oral assessments.
And another part of this poster that we have here is this idea idea of learning during an oral assessment. We think that's something that's not typically a part of traditional written assessments. And so on the poster here is just a short case study, a breakdown of one video in particular, where you can actually see in this 20-minute video pretty amazing leaps and bounds that the student is making in her understanding of this non-traditional multiplication algorithm. And she starts off with a very procedural knowledge of it. She then is able to link that procedural knowledge to procedural knowledge of a standard algorithm, and then eventually she's actually able to really well articulate place value and the role that place value has in the distributive property and why the standard multiplication.
So I'm Stan Yoshinobu from Cal Poly, San Luis Obispo, and I'm presenting a poster on the Spigot project. It's a National Science Foundation funded project where we are running workshops for faculty to come and learn how to use IBL in their own classes.
I'm going to talk to you a little bit about our graduate program at Lamar. So you can see here we got a few reasons why we think it'd be a good idea for you to pursue a master's degree at Lamar. One of the biggest things that I think is a good facet of our program is that we have really small class sizes, and we have about 15 faculty members, so you will really have a real relationship with any of them that you choose to get involved with. It's a good learning environment, a collaborative learning environment. We have a lot of our professors that use inquiry-based learning techniques in their own classes, and you'll have an opportunity that you might not have at a lot of other schools to actually be involved in teaching with a mentor at a very early level. This IBL apprenticeship program, you'd be paired with a Lamar faculty member in your very first semester and assist with teaching a course as opposed to just being thrown in. In the second semester, you will co-teach the course. That is, you will share the role of the instructor for the course. And then from then on, you'd actually be teaching your own courses. Beaumont has a low cost of living, and we have a $13,000 stipend. So hopefully that can be something that would make attending school a little bit easier. But we've had a lot of success with some of our graduate students. We have a couple students. My most recent master's student is now at Iowa State in Ames. We actually also have a student at NC State, North Carolina State, that graduated last year. There's really, like I said, I went to Lamar, so for me, it's home, and I really like it there, and I would say that it's a good place to really get your feet wet when it comes to graduate school. A lot of the things that we offer are very broad in scope. Like you wouldn't take 6 semesters of topology at Lamar, but you can take topology, you can take numerical analysis, you can take algebra, and so on and so forth. So it's a really good place to get your feet wet if you're planning to go on to get a PhD somewhere else, or if you just want to go teach somewhere. We have, like I said, a program set up that would be very, very instructive at a master's level that you would probably not be able to find somewhere else when it comes to instruction.
So this poster is describing all the different IBL activities going on at Harvard, and there's a wide range. Here we've used IBL to mean something that embraces a wide spectrum of learning techniques, so more active learning. A big feature I want to point out is the Masters in Mathematics for Teaching. It's a master's program for current teachers, and a core part of that program is each teacher has to take an inquiry-based learning class. The 2 main ones that they choose between are IBL Group Theory and IBL Graph Theory. All of our calculus classes are taught in small sections that really promote active learning and discovering the mathematics. We're developing a Harvard X class. Harvard X is an online platform that provides free open courses to the world. And what we're trying to do is integrate discovery of mathematics into an online platform, and we're facing certain challenges there. The Boston Math Teachers Circle is an outreach group to the local community teachers. It meets once a month, and we work on very rich mathematical tasks that have an access point for everyone, but lead to many different discoveries that are possible. Our Math M course at Harvard is a course that blends pre-calculus and calculus. So it takes a year to do the Calculus 1 topics, but at the same time we're doing the pre-calculus topics, so students have the time to discover what's going on. Teachers curate students' strategies for solving different problems. We're starting an Emerging Scholars program. The Emerging Scholars program is to help students who aren't necessarily set up for calculus, and they need a little more support. And this is with generous support from the EAF that we're doing this. And then we have a course for majors in the department, Mathematics in the Real World, which uses like very rich problems. And the whole course is really structured around students solving problems.
My name is John Boller, and this is my colleague Agnès Baudry. We are at the University of Chicago. Chicago has been supported by the Educational Advancement Foundation for over a decade now in terms of creating and developing and expanding our teaching of IBL courses. What we do is what the subject of this poster is. It's the courses that we teach, the way we teach the courses, a little bit of a sense of the content of some of those courses, the list of people who've participated in the teaching of these courses, and a little bit about our students. We didn't have enough data there. We certainly need more of that. But what I will say is that we do something that's pretty close to a traditional Moore method, in the sense that we think of these as we give our students scripts, the students prepare out of class, they come and present their theorems, the proofs to their theorems in class, we discuss those proofs, and then they take them home and write it up cleanly a third time. So we've had hundreds and hundreds and hundreds of students come through the 14 classes that we offer IBL style in any given year. We think of the honors calculus as the real bread and butter of our program. A lot of, it's 100 or so first-year students will go through the honors calculus sequence, and then about 20 to 25 students each in the number theory and geometry classes. We have a number of topics classes at the upper level that are at least in part taught IBL style as well. But I think one of the real features of our program is that you can see, just even by the length of this list, the number of graduate students, the number of postdocs, the number of people who have been trained to teach IBL via our center's activity is really something.
So I'm a second-year postdoc at the University of Chicago, and this year I got the honors of teaching our honors calculus sequence. So together with an advanced graduate student, so we always have paired a faculty member and a graduate student together. I got to teach 20 talented students. They all placed out of their calculus, computational calculus, or convinced somebody that they were enthusiastic enough to do this. And so we took them through the honors calculus sequence, which is from fall to spring. It's called calculus, but we don't actually get to calculus until the end of the winter quarter or the spring quarter. So what they learn through this is how to think like a mathematician. They come in not having ever written a proof for anything, and by the end of it, they write, like mathematicians with their own quirks, because they're 20 students and they develop their own style, which is also amazing. But by the end of it, they write like mathematicians, and whether what they're writing is right or wrong, it's usually they understand, they learn to understand why it's right and why it's wrong.
We are introducing a new technology called Learning Glass for inquiry-based learning. Learning Glass is basically a glass that the instructor uses a neon marker to write on, and then with the camera horizontally we flip the image. This gives a chance to the instructor to face the students, and the students can look at the instructor solving problems or discussing different scientific concepts or mathematical ideas. The preliminary analysis that we have done, we did an efficacy study last semester, and our finding shows that student learning gains correlate to how immediate they feel towards the instructor, or how they feel the instructor was present to them, and also how many times they logged in to interact with the instructor as he's teaching on the learning glass or she is teaching on the learning glass. And the poster that I'm presenting in this conference shows some of the preliminary analysis we did in that study and kind of introduce the technology. As you see in these pictures, the instructor is standing behind the glass, writing on a glass with a neon marker. And this technology was actually invented in San Diego State University with Dr. Matt Anderson. And with a camera, we kind of flip over the images. So what the students see, as you see right here, which is a snapshot of a video, they see the instructor writing properly, because with the camera we kind of flip the image. Some of the feedbacks we got from the students, they felt like they were with the instructor in the room. They felt like it was the office hours, they were talking to the instructor as the instructor was using the learning glass. And also, it gives a chance to the students to talk about problems. So not only instructor can use a learning glass, but even the students can discuss the difficulties and their problems. And I think those are the necessary elements of inquiry-based learning.
So my name's Naneh Apkarian. I'm coming from San Diego State University. And this is a poster about, it's almost a proposal for a study of mapping the community surrounding IBL. So one of the things that we know about IBL is that we have these conferences and there's a listserv, and it's a really supportive and engaged community and lots of people work together, but we don't really know what that looks like. And social network theory and social network analyses are something that we've been doing at San Diego, surrounding a few other things, and we're interested in trying to leverage those methods to build a better picture of how IBL techniques have spread throughout the community, and maybe learn something about how we can better spread them even further and like grow the community even more through the making and leveraging of different people's social networks and social relationships.
So we launched the Journal of Inquiry-Based Learning to preserve some of the historical notes, and we also wanted the opportunity for new IBL users to be able to publish their works and receive credit in a peer-reviewed published journal. So the Journal of Inquiry-Based Learning provides exactly that, a huge resource of complete sets of course notes. Can completely replace a textbook in any course. We have 37 courses represented on the site, and the materials are freely downloadable by any instructor. They are all classroom tested. They have been used in multiple times in multiple settings. The authors agree to mentor anyone who wishes to use the notes. Submissions are as they would be for any peer-reviewed journal. We have a template. The authors submit it. They are refereed. They go to a peer review process with blind refereeing, and assuming they're passed, they end up on the journal. The journal also has two other interesting collections. It has a collection of notes that were constructed at Guilford College many years ago, which are unrefereed but are of historical value, and it has many sets of notes from people who practiced the method for decades past, and those are also freely available but have not been through the refereeing process. So there are many sets of course notes for every course, from trigonometry, calculus 1 through 3, differential equations, linear algebra, group theory, ring theory, statistics, probability, voting. As managing editor, I coordinate all the efforts for the journal. As submissions editor, David Clark handles the submissions and the refereeing process.
My name is David Clark, and I am the other co-founder of the Journal of Inquiry-Based Learning in Mathematics, and I am the submissions editor. So if you're interested in, if you've got a course that you've taught and it works well, and you'd like to share it with other people, I invite you to write up a version of it and send it to me, and we'd like to consider it for publication in the journal.
I wanted to find out if IBL learning helped improve students' math grades going forward. So I decided to collect data from all of the institutions in upstate New York that are part of our IBL Consortium. So I checked with all the different institutions on what process I needed to go through. I had to apply for IRB approval, and as I did that, I ran across different requirements. Some committees wanted my submission to be online, some wanted to be an email, and one I even had a phone interview. So it was very different across all the different institutions as to what my IRB process was going to be. And now that I've gotten approval from most of them, I'm getting all the data coming in, and as I'm cleaning up the data, I'm noticing that students can take the same course. It's not necessarily IBL. I'm going to have to double check to see if it's traditional. But the third or second time that they take the class in the IBL fashion, they're actually passing it at a B or higher level, which is a surprising result. So hopefully once I've gotten all the data in, some are still coming in, even though I started this process in January of 2015, hopefully I'll get even more results in that same fashion.
So my name is Justin Dunmyre. I'm from Frostburg State University in Western Maryland. And what I'm presenting here is my reflections and my evolution of my flipped classroom. And so this is not entirely my idea. So David Pengelly came to a project next session, and he talked about this lecture textbook trap. And it goes as follows. My students do not read the textbook, therefore I must lecture. And as soon as my students see me lecture, they know they don't have to read the textbook. And as a result, we get stuck in an infinite loop. And so the idea then is to jump out of that loop by flipping the classroom into this 3-stage homework system. And so you can see I have a sample schedule here with some blue boxes around section 5.5. So those are the 3 assignments that are due for section 5.5. So the first one due is reading homework. And the reading homework is typically 1 to 3 questions, and I prefer a conceptual style. And those are submitted online through our course management system, which is Blackboard. And they're just graded on completeness. And I've had to update that a little bit. My first go around at it, the naive approach, was to just say, try it, you'll get the points. I wasn't convinced that they were really trying it. And so I changed that to get the 1 point, all answers are written in full sentences and are relevant to the questions. And then, the gradation of points going down. That drastically improved my responses.
Well, I'm Therese Shelton from Southwestern University, and we have done quite a bit with inquiry-based learning. Some of us have done it for a long, long time and kind of whole hog in a course. And I've been a little slower, but I do what I call injections of IBL, where I do some IBL in a lot of different classes. And so I didn't have any of these written up until I participated in a POGA workshop, and that really helped to give me a framework for getting the students to communicate the ideas that we had been trying to do. So for instance, this in an intro stat class, the students really got a better idea for what confidence intervals were, so that when they worked a problem in the book, everybody got the same confidence interval. They saw no variation in them. They didn't see any variation in the samples. But here, and I tell them that this is contrived, it's for educational purposes, because this is one where we know what the distribution is. But they can see, they have to tell me which one is for a sample of size 4, which one is for a sample of size 16, and they can do that very easily. And then they each roll their own set of dice and create a confidence interval with the bead in the middle representing the mean. And then they paste them on here in the position, and then they can say whether or not their confidence interval included the true mean or not. And then we see the overall class percentage so that they can get the idea of what a confidence level means.